Hello everyone. In our previous class, we started the discussion on hydrogen atom where we were discussing about the three-dimensional problem, which is the particle in a spherically symmetric potential. So we understood what actually is a spherically symmetric potential and had set a goal where our final destination was to find out that for such a spherically symmetric potential, the angular part of the wave function gives us a spherical harmonic, and the second goal was to show that the potential energy function is entering only in the radial part of the equation and it is absent in angular part of the wave function. So in order to get or reach this goal, we had separated the angular and radial part of the wave function corresponding to the particle in spherically symmetric potential. So today let us separately understand in depth about the concept, or let us reach our goal. So first one is to find out the solution of angular part of the wave function and to check whether it finally gives us the spherical harmonics. So what actually are the spherical harmonics? So generally these terms are used in mathematics and physics where the spherical harmonics are the special functions which will be defined on the surface of the sphere. Means in mathematical methods of physics, you might have studied the concept of different polynomials or special functions like Lagore polynomial, Hermite polynomial, Legendre polynomial, all these things. So when you solve for or when you search for the solution of angular part of the wave function corresponding to the particle present in the spherically symmetric potential, finally the solution should consist of the spherical harmonics, means there should be a special function included in the solution of this. So whether it is there or no, let us check it out. So in our previous class, if you have not gone through the class, first go through it, then continue here. So xi of r theta phi, which we had taken as the wave function corresponding to the particle in spherically symmetric potential, where we had derived all these things in polar or spherical polar coordinates, we had splitted the wave function into three parts, or as such you can say into two parts. So r of r is representing the radial part and theta and phi both are angles. So theta of theta and phi of phi combinedly we can say they are nothing but the angular part of the wave function. So using the previous knowledge, we have already derived separately what are the solutions for r of r, theta of theta and phi of phi. So first let us study about the phi equation. So equation number A, which was denoted in our previous class, gives us the phi equation, which is nothing but d square phi by d phi square plus m square phi is equals to 0. And the corresponding solution for this second order differential equation is nothing but phi of phi is equals to a into exponential of plus or minus I into m into pi. So let us call it as equation number A with a small letter. Then this wave function or the angular part of the wave function, which is denoted as phi, has to be single valued because finally it is a wave function and the condition for validity of wave function is that it should be finite as well as single valued. That's why if this phi has to be single valued, means phi of phi can be equal to phi of phi plus 2 pi, where it is going to be with respect to the periodicity. So when you do it, if you substitute this in your equation small a, we get a into exponential of plus or minus im pi is equals to a into exponential of plus or minus im into, in place of pi we are putting phi plus 2 pi. So when you solve it, a and a is going to cancel out exponential of plus or minus Im pi is going to cancel out, and we are remaining with exponential of plus or minus Im into 2 pi is equals to 1. And when you solve it, it is in the form of e raised to I theta, which is nothing but cos theta plus I sin theta, or else e raised to minus I theta, which implies cos theta minus I sin theta. So in place of theta, if you just put the value of 2 pi m, we can find out when this condition is valid. And the condition will be valid, that is exponential term will be equal to 1 only when m takes the value 0, 1, 2, 3, so on. So here we define this m as the magnetic quantum number. Then coming to the next part, in the wave function, that is phi, which is defined as a into exponential of plus or minus Im into pi, we have a, which is a constant, which we say as a normalization constant, and we need to find out what is the value of a. For that we need to use the normalization condition, which is nothing but integration from minus infinity to plus infinity of the wave function conjugate into the wave function itself in that domain, which is equals to 1. So here in spherical polar coordinates, we know that pi is going to vary in between 0 to 2 pi. That's why the limits are going to change from minus infinity to plus infinity to 0 to 2 pi. And when you put the value of phi star and phi, we can just take a into a star outside, which can be denoted with a modulus sign with a square. And when you simplify the integral, we can observe it is in the form of e raised to x into e raised to minus x. So when you solve it, it is equal to e raised to 0, which will be equal to 1. So when you just integrate, integration of d phi will be equal to phi itself. Then the limits are from 0 to 2 pi. So upper limit minus lower limit, we get the integral to be reduced to 2 pi. So when you substitute the value, we get square of mod of a is equals to 1 by 2 pi. So a will be equal to 1 by root 2 pi. So this is the normalization constant, and finally the normalized wave function or the solution for the phi equation will be equal to 1 by root 2 pi into exponential of plus or minus Im into phi. So let it be equation B. So this is the solution for phi, which is again normalized. So this is one part of angular solution of the wave function. Then coming to the second part, that is with respect to theta. So in our previous class we have seen what is the solution for theta. So that was denoted by equation capital B, that is theta equation is equals to 1 by sin theta into d by d theta of sin theta, d by d theta of capital theta plus lambda minus m square by sin square theta into capital theta is equals to 0. So in order to solve this, let us consider z is equals to cos theta. And when you do that, when you just differentiate, we get dz is equals to minus sin theta into d theta, because differentiation of cos theta is minus sin theta. And in the equation B, we need the value of d by d theta so that we can substitute it back. That's why d by d theta can be written in terms of z by using the chain rule. So d by d theta will be equal to dz by d theta into d by dz. So this is nothing but the chain rule, and from the above equation z is equals to cos theta. So dz by d theta will be equal to minus sin theta. So the same thing is substituted and multiplied by d by dz as it is. Then from this equation only we can write what is the value of sine theta. So cos theta can be written in terms of sine theta, that is 1 minus z square whole raised to 1 by 2. So that is a standard equation. So sine theta is nothing but square root of 1 minus cos square theta. The same thing, cos theta is represented as z here. So substituting, we get d by d theta value as minus of square root of 1 minus z square into d by dz. Now just that we need to substitute all these value in equation B. We get 1 by sine theta as 1 divided by sine theta is nothing but square root of 1 minus z square into d by d theta is nothing but minus of 1 minus z square raised to 1 by 2 into d by dz, then multiplied by sine theta. So from this equation itself we can say sine theta is nothing but 1 minus z square raised to 1 by 2 and multiply by d theta of capital theta. So again d by d theta is minus of this value. So minus I have written here and taken as it is, plus lambda minus m square divided by sine square theta. So cos square theta will be equal to 1 minus sine square theta. That's why sine square theta will be equal to 1 minus cos square theta. So 1 minus z square into capital theta will be equal to 0. So here we can observe that some terms are going to cancel out and we get d by dz of, so it is something like root x into root x, it will be equal to x, d by dz of 1 minus z square into d theta by dz plus lambda minus m square by 1 minus z square into capital theta equal to 0. So this is taken to be equation number small c. So this equation is the same equation which we observe in associated Legendre equation. So when we solve for Legendre polynomials, we get the same equation where z is equals to cos theta and the equation is represented as this, which is equation number C. And they will be having the pole, that is extremum points at z is equals to plus or minus 1. So if there should be any physically accepted solution for this Legendre polynomial equation, then we say that lambda is taken to be equal to L into L plus 1 and L is having the value 0, 1, 2, 3 so on, whereas M is represented in terms of L as M is equals to 0, plus or minus 1, plus or minus 2 so on up to plus or minus L. So M is the magnetic quantum number. Let us see what actually is small l. So here the solution for equation C is Legendre polynomial PL of z if m is equals to 0, whereas if m is not equal to 0, then the solution will be that of the associated Legendre polynomial. So this is what actually we have already studied while studying mathematical methods of physics. If you just go through it, that is, understand the concept of Legendre polynomial, all these results are obvious. Then again we need to find the solution, and from the polynomial itself we know that the solution for theta will be equal to NLM into PLM of z. So here NLM is nothing but normalization constant. So our next task will be finding out what is the value of NLM. So again we need to find out that value, means we need to use the normalization constant, normalization condition, which is nothing but integration from minus infinity to plus infinity of the wave function, that is theta star into theta into dz, which will be equal to 1. So now if you substitute the value of theta, finally you will get the equation in this form, and here the extremum points or the limits of integration will be from -1 to +1, that is according to Legendre polynomial. So from the same we have the orthogonality relation for associated Legendre polynomial, which is nothing but the integral will be equal to 2 by 2l plus 1 into l plus mod m factorial divided by l minus mod m factorial into delta lk. So this is the orthogonality condition for associated Legendre polynomial, and we are making use of the same in order to find out the normalization constant. So just we are using this orthogonality condition, and the same value will be put in normalization condition. So in place of this integral we are writing the solution, and it is equated to 1. And when you just rearrange it, we can find that n is equals to epsilon into square root of 2l plus 1 into l minus mod m factorial divided by 2 into l plus mod m factorial. And we need to define this epsilon, and if m is greater than 0, that is m is positive, then epsilon is nothing but -1 raised to m, and if m is less than 0, then epsilon will be equal to 1. So now substituting the value of normalization constant in our theta equation, we get theta solution for the theta equation, which is theta of theta is equals to epsilon into square root of 2l plus 1 into l minus mod m factorial divided by 2 into l plus mod m factorial into PLM of cos theta. So this solution is taken to be equation D. Next, coming to the actual part, that is we need to find out the solution for angular part, and angular part consists of theta solution as well as phi solution. So just that we need to combine these two. So when you combine equation C and equation D, we get the normalized angular part of the wave function. So if it is represented as YLM of theta comma phi, then just putting the value of the theta solution as well as phi solution and simplifying, we get the angular solution of the wave function, which is YLM of theta comma pi is equals to epsilon into square root of 2l plus 1 into l minus mod m factorial divided by 4 pi into l plus mod m factorial into PL of cos theta into exponential of Im phi. So here only root pi is taken inside, so that 2 into 2 pi will become 4 pi. Again here L is nothing but 0, 1, 2, 3 so on, and M is equal to 0, plus or minus 1, plus or minus 2 and so on. So the solution of angular part of the equation, here it is called as spherical harmonics, because it is depending on a polynomial function or a special function, and it is independent of energy capital E as well as the potential energy V of R. So first goal is reached, that is we have derived the solution for angular part, and we observed that the solution gives us spherical harmonics. Then coming to the second goal, that is we need to see that, or we need to show that the potential energy functions enter only in the radial part of the equation. So already we have found out the radial part of equation, which is equation number C in our previous class, and here we are going to define a new function, that is r is equals to xi of r divided by small r. So r is again a function of small r and xi is again a function of small r. So here by this we get a new radial function, which is xi of r is equals to r into r of r, and this will be substituted in the above equation, so that, or if you just use this wave function, that is the new radial function, in our Schrodinger equation, we get d square xi by dr square plus 2m by h cross square into e minus v of r minus l into l plus 1 into h cross square by 2 mr square into xi equal to 0. So actually, when we had considered capital R as the radial part, we had only two variables or two energy terms, that is E minus V of R. But here for the new radial function, we are having a additional term, which is nothing but, we consider this total term as effective potential term, that is V effective is equals to V of R plus L into L plus 1 into H cross square by 2 mr square. So this second term is nothing but the repulsive term, whereas V of R, generally we say it is a Coulombic potential, so it is an attractive term. So finally we are having the effective potential as the contribution of both attractive as well as repulsive potential. So if you look at this repulsive term and if you just modify, you can get the repulsive force also. So repulsive force will be equal to L into L plus 1 into H cross square divided by mr cube. And as it is a repulsive force, you can again define a centrifugal force in this case. So centrifugal force is nothing but mr omega square, and if you just want to convert it in terms of above, that is mr square into omega whole square divided by mr cube. So what we have done here, we have just multiplied and divided by mr cube. So finally we get this term only. So when you multiply by mr cube, here we are having m square, and r square whole square will be equal to r raised to 4 divided by r cube. Again it is going to be r itself into omega square. So why we are writing this in this form is that, so that we can explain centrifugal force in terms of capital L, where capital L is nothing but the orbital angular momentum. So whenever you are having the spherically symmetric potential, so if you consider the example of hydrogen atom or hydrogen like atom, so at the center, that is a fixed point, you are having a positive core, whereas the electron will be revolving along the circumference. So because of this rotation, again there is a angular momentum, or which we define as a orbital angular momentum. So the same concept is applied here, and we are representing centrifugal force in terms of orbital angular momentum, so that finally we can define what is actually small l. So when you compare this repulsive force and centrifugal force, so the nature are same, so both can be equated, and we can see that if you compare these two terms, that is repulsive force and centrifugal force, both are forces, so both can be equated. We can see that in the denominator we are having mr cube itself, and in the numerator L square is equals to L into L plus 1 into H cross square. So if you just rearrange, you get L is equals to, that is capital L is equals to square root of L into L plus 1 into H cross. Generally, we just say capital L is equals to L into H cross, but the actual or the precise value of orbital angular momentum in terms of these quantum number small l is square root of L into L plus 1 into H cross. So based on this, we can explain what actually is small l. So L is taking the value 0, 1, 2, 3, so on, and it is nothing but a quantum number. So as this quantum number is related to capital L, that is nothing but orbital angular momentum, we call small l as orbital angular momentum quantum number. So m is magnetic quantum number, whereas L is orbital angular momentum quantum number. So both the quantum numbers we have defined, and we need to stress on the concept of potential, which is coming in the equation of radial part of wave function. So here we have observed that V effective or effective potential is sum of attractive potential V of R and repulsive potential L into L plus 1 into h cross square by 2 mr square. So if you plot a graph of V effective as a function of R, we can observe this type of nature. So this nature we have come across while we study Lennard-Jones potential. So if you just can recall, it is very good, or you can just go through it. So in Lennard-Jones potential we observe that when the potential is negative, it is showing this curve, that is attractive nature. This curve is for attractive potential, whereas this steep curve is representing the repulsive potential. So what we observe here is that if you consider V of R in this effective term as the attractive potential given as Coulombic potential, which is nothing but minus Z into Z dash E square by R, then the repulsive potential, which is given as L into L plus 1 into h cross square by 2 mr square, is going to be negligible at large distances and dominant at closer distances. So what happens here, whenever there is a Coulombic attraction, when you compare these two equations, at large distance means R is going to increase. So in the denominator you are having R in case of V of R, and in repulsive potential you are having R square. So as this R is going on increasing, R square is going on increasing, so as it is in denominator, the whole term is going to be very small. So that's why we say that at large distances the repulsive potential is negligible and attractive potential dominates. That's why at large R values, here R is going on increasing. So at larger R values, that is the distance is going on increasing between the fixed point and the particle which is moving in the circular orbit, then we observe V of R as dominant, that is attractive potential is dominating. That's why we can observe that V effective is having the negative value. So if it is above, it is positive, then it will be repulsive interaction. And this repulsive potential will be dominant at closer distances, because if R is less, then we get this term as greater term because it is depending on R square. So when R is small, that is when the distance between the particle and the fixed point is less, we can observe that repulsive potential is greater. So based on this graph, we can say that as the orbital angular momentum quantum number, that is L, is going on increasing, that is from L is equals to 0 to 1, 2, 3 and so on, the depth of the effective potential, so this is nothing but the depth of effective potential, is going on decreasing. So as L increases, effective potential depth is going to decrease and its minimum, that is the minimum position, is going to shift away from the origin. So this is origin. So here for L is equals to 1, the depth or minima is near to origin when compared to for the curve at L is equals to 2. So why this happens? So based on this we can explain the boundness of the particle. So as the particles are away from the origin or from each other, then they will be of the form which are of lesser bound in nature. So the particle will be less bound because As the particle's angular momentum goes on increasing, the particle becomes less and less bound. That is the meaning of it. So as the angular momentum, that is, if this L is going to increase, means again L square is going to increase. Based on that, if L square is or L is greater, the particle is lesser bound to the fixed point. So that's why we say whenever a particle, that is if you consider a hydrogen atom, you are having the fixed point, that is a positive core separated from the electron. The distance is small, that's why we say both are tightly bound. So you can't easily separate it. But if you consider a larger molecule, easily separation can be done because they are lesser bound. So that is defined based on this effective potential. And another one you can think is that En, that is energy eigenvalue for such a system, is 2L plus 1 fold degenerate. So in our previous slide we just saw in that wave function term we are having square root of 2L plus 1. So the energy eigenvalue which you represent as En is going to be 2L plus 1 fold degenerate, because for a given L value there are 2L plus 1 different eigenfunctions which again correspond to the same energy itself. And this degeneracy or this property is a special feature or a peculiar feature of spherically symmetric potential, which is also called as central potential. So this is almost all the details about the particle in a spherically symmetric potential, where in our first class we separated the radial as well as angular parts, and in today's class we just saw that the angular part gives us the spherical harmonics, whereas the radial part consists of the potential energy term which can be defined with respect to effective potential, where we understand about repulsive potential as well as attractive potential, and finally graphically interpreted, as well as we understood why L is called as orbital angular momentum quantum number. So this is for today's class, and in our next class we will be dealing with the reduction of two body problem into a single particle problem. Till then, study well. Thank you.